So how do we recover these representations? How do we derive these representations from large quantities of unlabeled data? In a moment, I'm going to describe the mechanics of the Brown clustering algorithm, but firstly I want to talk about the intuition which underlies this algorithm. The intuition is that if we have a large amount of unlabeled data, we can leverage the fact that similar words tend to appear in similar contexts. Or a little more precisely, similar words have similar distributions of words to their immediate left and right. So, for example, if I take the word "the" and the word "a," these are both they're similar words, they're both determiners. I can look at the frequency of different words to the immediate left and right. So I might find that prepositions like "in" and "of" are frequently seen to the left of the word "the", that nouns like dog or park or share are frequently seen to the right. And so you can, given a large quantity of unlabeled data, you can basically look at the distribution of words to the immediate left of the word and the distribution of words to the immediate right. And I can do a similar thing for the word "a." And because these two words are similar, I'm going to see a very similar distribution, or at least a somewhat similar distribution, where again I see the most frequent words being nouns like dog, park, or share to the right, and prepositions like "in" and "of" to the left. If I take another example, if I take Monday versus Tuesday, if I look at the frequent words to the left, they're going to be things like last, or on Monday, last Monday, various things here. And again, we're going to see these words like last or on frequently in this context. And similarly, there'll be a set of words which tend to appear after days of the week, and we'll see a similar right context for both Monday and Tuesday because they are both days of the week. So that's the basic intuition. And the Brown clustering method is one clustering algorithm. There are actually several possible algorithms. We're going to focus on this one. But all of these different ways of deriving these word clusters basically leverage this intuition that similar words tend to have similar distributions of words to the left and right. So now let's look at the formulation underlying the Brown algorithm. So we'll use script V to refer to the set of all words seen in the corpus, i.e. this is going to be our vocabulary, and we'll assume that the corpus consists of a sequence of words W1 through W capital T. For convenience, I'll assume that we don't have individual sentences, we just have one very long sequence of words. Think of this as the entire corpus concatenated. It's a minor detail whether we split this into sentences or not. And the output of the Brown clustering model for now is going to be a clustering. A clustering is a function C that maps the vocabulary to the set 1 through K. So every word in the vocabulary is going to be assigned an integer. So say K equals 1,000. We have 1,000 clusters. We might assign the word "the" to 1, "a" to 1, and then maybe Monday to 2, said to 3, and so on. So this function is going to map each word to an integer between 1 and 1,000, say, basically defining a mapping from words into the underlying classes. So in the Brown model, there are basically two types of parameters, and they look very similar to the types of parameters we would see in a bigram HMM. So firstly, we have emission parameters. So we might, for example, have E of the given 1, which intuitively is the probability of cluster 1 emitting the word "the". Okay, so each cluster from 1 to K is going to have a distribution over the different words in the vocabulary. The second type of parameter looks very much like the kind of transition parameter we saw in HMMs. So for example, Q of 3 given 1 would be the probability of class 3 following class 1. So a Brown clustering model is going to consist of a function C that maps the vocabulary V to the set 1 through K together with these parameters, these E and these Q parameters. It's really very similar to an HMM. The main difference is that this function C is deterministic, that each word gets mapped to a single state. We're not going to allow any ambiguity where different words, or rather the same word, can belong to different states in the HMM. Now, given settings for these parameters E and Q, and given a definition of this function C, we can write down the probability of our corpus as follows. It's going to be a product of terms, I equals 1 to n, and we're basically going to have a bigram model, wi given wi minus 1. That's what this term here is. But to calculate this, we calculate this in a rather different way from what we've seen before. So there are two terms. Firstly, I have Q of C of wi given C of wi minus 1. That intuitively is the probability, given that the previous cluster was C of wi minus 1, of choosing the next cluster as CWI. And then I have E of wi given C of wi minus C of wi, sorry. That's what we have here. So you can think about this as follows. Say the previous word is say this is wi minus 1, and I want to calculate the probability of the next word being dog. And let's say, for the sake of argument, that C of